Okay, so in this session, I wanna introduce the pressure prism concept to you, and it's another type of calculation, kind of calculation for the hydrostatic forces on vertical planes that you can use. Okay, instead of using the kind of in moment of inertia concepts that we learned before, this is a little bit simpler way of calculating it just by kind of geometrical relations. So let's get started. So we have example here, and in this example that is shown here, we want to find what is the magnitude and location of resultant force on the attached plane. Okay, so we have a plane here, and we want to see, and we have water up to this height, and we want to see what is the magnitude and location of the force on this attached plane that we have here. Okay, so let's get started. So answer. So now I want to use the pressure prism concept, and what it means is as follows. So we have this plate here which has 0.6 meter length, right? So let me just show the force body diagram of that. So say we have this. So this is this plate from side view, that plate from side view. So we have water. So this is 0.6 meter from here to here is 0.6 meter. Okay, and then we have 2 meter above that we have water, right? So we have up to, say here we have water, 2 meter. We have some water on top, and then here we have the free surface, and then we also have the pressure of the top of that, which is P equals to 500 kilopascal, which is given to us from the problem here, right? So this is kind of just this problem from the side view. I'm just plotting it from the side view, and then now I want to show the pressure, hydrostatic pressure forces that are acting on this plane. So here, I'm gonna calculate this, but here you can see, because we are of 2 meter below water, the surface, free surface of the water. So here we have a force which is rho g h1, which is times 2, right? And this is rho water. And then at the bottom we have a larger force because we are going to a greater depth, right? So my force is going to be something like this, where we have is the magnitude of that is going to be rho water g times 2 plus 0.6 meter, right? 2.6 meter because we are 2.6 meter from the top of the from the free surface level, right? So this is 2.6 meter. Okay, and because this is a compressible fluid at rest, we can assume again the linear change in hydrostatic pressure. So we are going to have this linear relationship here, and this is going to be the free body diagram of the force, hydrostatic force that acts on this attached plane. Okay. So the prism concept states that we can decompose this total force into two forces. Okay. One, we can say it has a triangle like this. So this is the triangle. So it includes from this triangle, plus we can superpose it with a rectangle. So let me put it a little bit here. Plus a rectangle okay, and then find the forces by this decomposition. Okay, so what I'm gonna do is I'm gonna find the resultant force Fr and its location, so the magnitude and the location of it for each of these two components. Okay, and this is a technique you can also use in this kind of problems. So we are going to have first F1, which is the total force that is exerted on the plane by this rectangle. So I'm going to just show it as F1. And then we are going to have F2, which is the total force that is exerted by this triangle and this attached plane. So the total force Fr is going to be the sum of F1 plus F2, right? Okay. So let me start. So what is the value of F1? The magnitude of the F1. So F1 is going to be, F1 is just the value of the force up to here, right? So this and this equals, okay? So it's gonna be the value of the pressure at this point here. So we have water. So we have water, which is gonna be rho g h1. If we assume this is h1, so let me just write it as times 2 meter times 2. And then we have to add the free surface pressure for if we want to calculate the absolute one. And because here it is given to us, I'm gonna just add it. If it was not given, I would have added, but now because this is given here, I'm gonna just add also the atmospheric, the air pressure here. So this is P air on top of that, okay? So I'm gonna have plus P air, and this is gonna be the pressure, and in order to get the force I have to multiply it by the area. So multiply it by the area of the attached plate. Okay, so let's now calculate this. So I'm gonna have, what is the rho of water? Rho of water is 10 to 3. Then we have kilogram per meter cube times G, which is 9.81 Newton per meter cube. The whole thing is Newton per meter cube, so it's gonna be meter per second square. And then we have 2 meter. And then plus 550 kilopascal, which is going to be 550 times 10 to the power 3 Newton per meter square. Okay, and then multiplied by the area. I think I didn't give the area, so I have to give the area of the plane, area of the yeah, I mean, you can just imagine this is a rectangle, this is a square attached. I had to mention it, attached square plane. So then the area is going to be 0.6 times 0.6. So it's going to be 0.6 meter times 0.6 meter, or 36.36 meters square, which is gonna be 2.51 kilonewton. Okay, so this is the magnitude of force 1 here. And then let's calculate the magnitude of force 2. So force 2 is gonna be, the magnitude of that is gonna be like this. We can calculate it like this. So we have here we have rho g times 0.6 meter, right? Because this is 0.6. Okay, and in order to, for you to, if you want to just use the previous one, so here you see it is 0.6, so I have just written 0.6, but this is also equals to and as you see, this is what we had here, right? Because here we had, let me write it down here. So here we had, let me write, is P air plus rho g times 2.6, right? This was the magnitude of the force at the bottom here, okay? If you subtract the magnitude of the force at the top, which is gonna be P air plus rho g times 2, right? If you subtract this from this, right, these two are going to cancel out. P air is going to cancel out, so I'm just going to remove that. And rho g is going to be rho g 2.6 minus 2, which is going to be rho g 0.6 meter, right? So that is what I have written here. Okay, so it's going to be rho g 0.6 meter, and the amount of the force is going. This is the pressure, right? From it starts from 0 to 0.6 meter, rho g 0.6 meter. So the force is going to be So the force is gonna be, because this is a triangle, I have to calculate the area to get the sum of all these small pressure elements, right? So it's gonna be rho g 0.6 meter plus, it's gonna be 1/2 of that, right? So let me write it down here. It's gonna be 1/2 of, because you want to calculate the area of this. So let me just give you another example. So say you want to calculate the area of this rectangle, okay, which is this. So you have here A, and you have here B. Okay, so here let me give a better example. I think this is not better, good. So let's say if you have a full rectangle, okay? So if you had a full rectangle, here with rho g 0.6, okay, what would have been the total for the average pressure here? So the average pressure times, and if you have like A here, the total force is going to be rho g 0.6 times A, right? And now imagine that we remove half of this pressure, like we only consider a triangle here, okay, something like this. So we throw away half of this, which is this force from here to here. So if I want to calculate the area, the force of the blue one, which is going to be rho g 0.6 A over 1/2, right? Because this is 1/2 of that. I throw away half of it. So here is the same thing. This is also a triangle. So I need to just multiply it by 1/2 to get the force for the correct force for this triangle. So it's going to be 1/2 rho g 0.6 times A, right? So this is how you can calculate it for a rectangle, for a triangle. So all the time always when you want to calculate, for example, for this kind of triangles, you can calculate first for a full rectangle and maybe divide it by half, right? Because you only have half of it, okay? So this is gonna be 0.6 meter over 2 times 10 to power 3 times 9.881 Newton per meter square per meter cube times the area, which is 36.36 meters square, and this is gonna give me 0.95 times 10 to the power 3 Newton. Okay, so we have the value of F2 and F1, and the value of their total resultant force is going to be the sum of these two, which is going to be F2 plus F1, right, on this plane. So I just write it down. It's going to be F1, the magnitude of the F resultant force. It's going to be F1 plus F2, which is going to be 26 point, I think I wrote it down wrong here. It is gonna be 25.1 kilonewton. So it's gonna be 26.1 kilonewton. Okay, so this is the result, the magnitude of the resultant force. And now how about the location? So let me calculate the location. Let me write it down again. F1 plus F2. And this is gonna be 25.1. It's gonna be 26.1 kilonewton. Okay, so vertical location. So vertical location of FR. So the horizontal one is clear, is gonna be here, right in the middle, because there is a symmetry. We have a symmetry here, so it's gonna be in the middle, but we don't know where is the vertical kind of location of it. Okay, so let's find the vertical location. Okay, so in order to find a vertical location, I can use this technique again for calculating the momentum. So if we have y here, vertical direction, say from the bottom, from here, if this is O, okay, you can determine it yourself. Okay, so we have two forces that are acting on here. So one is F1, which acts where? So we have F1. This force acts in the middle, right? This is gonna be in the middle. So this we are gonna have, it's gonna be 0.3 meters. And this one is gonna act the average of that. If you have it from the triangles that we know, it is gonna be 1/3 of this side, right? This is gonna be 1/3 of it this side. So this acts at 0.2 meter, which is 1/3 of 0.6 meter, right? So for a triangle, we know it's gonna be, for this type of triangles, which have a which have this 90-degree angle, their force acts at B, if this is B over 3. Okay, so this is, we know from previous lectures. So this one acts, if we have, this is the O at the bottom of that, this acts at 0.5 meter. So let me do it here. This acts at 3 meters. And the second one, which is F2, is a smaller force. F2 acts at 0.2 meter. So this is F1, acts at 0.2 meters. And F4, which is going to be the sum of these two forces, should act somewhere in between these two, right? So it should act somewhere here. This is going to be FR with location of YR. Okay. So now I want to calculate the location of that. So I calculate the moment around O. So the moment around O of both forces should be the same. So FR, the resultant force, should create the same moment as F1 and F2. This is F2. So FR times YR should equal to F1 times 0.3 meter plus F2 times 0.2 meter, right? I am writing the moment around O. Both of them should give me the same moment, okay? So YR, or the location of this resultant force, is going to be F1, which is 25.1 kilonewton, times 0.3 plus F2, which is 9.954 times 0.2 over FR, which is 26.1 kilonewton, and this is going to give me 0.296 meter. So the location of the force, the location of the magnitude of the resultant force is this, and the location of it is going to be 0.296 meter from the bottom of the plate, which if you calculate it is going to be 2 meter from here plus 0.6 minus 0.296 meter, which is going to be around 2. Let me just calculate it. It's going to be 0.6, so it's going to be 0.304 meter from the free surface level. Okay, so this is going to be the location of that, and the magnitude of it is going to be through this F1 plus F2. So this is the prism concept, and that means that for this type of problems where you have these complicated hydrostatic distribution shapes, what you can do is that you can decompose it into two components, 2 or 3 simpler components depending on the problem, and then calculate the force, the magnitude of the force, and where it is applied on the plane separately, and then kind of combine them together. So decompose it and then superpose all of this together. So here we calculated first F1 here, which was a rectangle, this rectangle here, right? And then we calculated this, the force, the contribution of this triangle here, okay? And so by this will kind of simplifies our solutions. So this is F1 we found, and F2, which is gonna, and then the FR, the resultant force, is gonna be the sum of these two forces, okay? And the vertical location of that, you can find it by writing a simple moment equation. So the FR times YR, you can calculate it from here, or you can even calculate it from this origin, O prime, from the free surface. And then that will give you the YR from the free surface, okay? So you're free to use any of them, any coordinate system you want. They should give you, both of them will give you the same location, and both of them should give you the same location of the resultant force, okay? So this is a technique which was very useful for calculating the this kind of hydrostatic forces. So now in the next example, I want to solve I want to calculate hydrostatic pressure force on a curved surface. Okay. So the problem that we have is as follows. Determine the magnitude and line of action of the resultant force that the water exerts on a 2-meter length of the curved section BC of conduit wall. So we have a wall here, and then we have some water in this channel, which is only filled with half water, and you see the free surface. So this is filled half. You see the free surface here. And so I want to calculate the force, the hydrostatic force, that is applied to this section, okay? 2-meter length of this section, okay? So the first thing I need to do is to draw a free body diagram and then calculate the vertical and horizontal forces on this that are exerted to this curved surface or curved section, okay? So I will do it, let's have a break, and then I will do this in the next session. I will solve this in the next session, and also after that I am going to talk about the buoyancy principle after solving this question.